Hello. In the previous lecture, we have introduced the concept of autonomous agents, and we have closely looked at the line of sight test, which is a key technique for autonomously moving agents. But this technique does not create any movement by itself. It is applicable to agents which are already in motion in some way. For example, following a fixed path, like in this sample project called Girl, or even being directly controlled by the player. This time we will be talking about another technique called behavior patterns, which can create the actual movement. Moreover, they are one of the most fundamental techniques used in AI to control the NPCs or non-player characters in many different games. For example, they allow for modeling the effective enemy pursuit behavior, but also flee or evade. But before we go on, we have to learn something about rabbits and their natural archenemy, the fox. We will consider both the rabbit and the fox to be autonomous agents. And here is a quick reminder about autonomous agents. They can sense the environment and act upon this environment, and doing this, they do it in pursuit of their own goals. So to affect what they can possibly sense in the future. So, what is the meaning of being a rabbit? Rabbits, as autonomous agents, are normally nibbling some grass. Sometimes they notice that the world state has changed, and this happens when they sense a fox. They act by fleeing in the opposite direction to the fox, and this is done to minimize the chance of further sensing the fox. And now the meaning of being a fox. They are just wandering around, but sometimes they can notice that the world state has changed, the rabbit has been sensed. So they act by pursuing the rabbit to maximize the chance of still sensing the rabbit, and consequently to change their own state from hungry to full up. In this context, I can now discuss our behavior patterns such as seek, flee, arrive, pursuit, evade, wander, and obstacle avoidance. Swarm intelligence is a little bit broader topic, and it will be left for a separate presentation. But first things first. This diagram shows a moving autonomous agent. The direction and speed or velocity of this movement is shown as a velocity vector. The agent acts upon its environment using a steering force, and this steering force is introduced in order to change its current velocity to the new desired velocity. This desired velocity can be read from this diagram as a simple vector addition. So velocity plus steering equals desired velocity. Our controlling task in every frame of simulation of a moving autonomous agent is to find the value of steering. And this value of steering can be found from this formula: desired velocity minus velocity or current velocity. If the value of steering is large, the change in velocity will be aggressive. So to keep it reasonably low and to achieve soft fluid motion, you should apply reasonably low values of steering as well. With this basis, we are at last ready to discuss the first of the behavior patterns, the Seek behavior pattern. It is exactly what a fox demonstrates on spotting a rabbit. It tries to change its current velocity so that to get closer. So here we have our autonomous agent. You can think about it as a fox with its current velocity, and now it spots something that it wants to seek. For example, rabbit. Therefore, its desired velocity will be pointing towards the desired goal. And having this, we can follow on with the calculation of the steering force, which will be exactly as shown in the previous slide. Let's have a look at some pseudocode, which is nearly C++, but in order to make it a working code in GFC, you may need some slight modifications. So first of all, we will define two vectors, desired velocity and steering. The assumption here is that the velocity is the input for this algorithm, so I don't declare this as a separate variable. Now, desired velocity can be calculated as the relocation vector or the relative position of the target in relation to our current position. So it's target position minus position, where the position is the position of the agent. Then the desired velocity has to be normalized, because we don't want a very high desired velocity just because the connection of the relative position of the goal is far away. Okay, so by normalizing the desired velocity and multiplying it by speed, the desired velocity will keep the constant speed of the movement. And now we can calculate steering using the formula shown in the previous slide as desired velocity minus velocity. And these three lines of code is actually everything you need in order to get the Seek behavior pattern, which is very useful, for example, to model enemies in a game. The next behavior pattern is called Flee, and this time is what a rabbit does on spotting a fox. So again, we have a agent. This time it would be a rabbit, and we have some kind of a goal, but the difference now is that the agent wants to move away from this object here. Therefore, the desired velocity will be pointing this way. Okay, but apart from this detail, everything else is exactly the same as previously. So the steering force will look quite strange. It's going backwards, but the maths behind the scenes is exactly the same. Steering is still desired velocity minus velocity. And here you have a pseudocode, which is very similar to the pseudocode of the Seek behavior pattern. The only change is that desired velocity is now calculated as position, my current position minus target position. So it's negated value of previous desired velocity, which was target pos minus pos. So Seek and Flee are really similar in terms of coding and in terms of maths, but so different in terms of behavior in a game. The arrive behavior is very similar to the Seek behavior. The difference is that the Seek pattern always applies the same constant speed, and sometimes it happens that it overruns the desired destination, particularly if the latter is stationary. Arrive is an enhanced version in which the speed is fine-tuned to allow a smooth arrival to the destination point. As you can see from this pseudocode, the speed is made proportional to the distance between the agent position and the target position. Therefore, when the agent gets closer to its target, its speed will get lower. Pursuit is another enhanced version of the Seek behavior. This time, the target point of an agent, called here pursuer, is located in front of the other agent, called evader, and exactly in its anticipated future position, so that the pursuer, instead of heading towards the evader, it tries to forestall or anticipate its future position and go directly to this expected position. This creates much more lifelike behavior than in case of the seek pattern. And the evade behavior pattern is to pursue what is flee to seek. So this time we are steering the evader, but instead of avoiding the pursuer, the evader tries to avoid the anticipated future position of the pursuer. The next behavior pattern is called wander. Wander is a very useful, even though not particularly exciting pattern. It is designed to produce an impression of random walk through the agent's environment. A naive approach would be to calculate a random steering force each frame of the animation, but the movement produced by this would be very jittery. So to have a little bit more persistent turns, there is another solution, and it is to project a circle in front of the agent and steer towards a special target that is moving along the perimeter of this circle. Here is our agent, and this is the circle projected in front of this agent. We will call this circle simply a wander circle. The algorithm is well parameterized by the radius of the circle and the distance between the circle, the center of the circle, and the agent. Now, the first step of the algorithm is to initialize the target position. This target will always be somewhere on the perimeter of the circle, and it's quite logical that the first initial position for the target will be in front of the agent at the opposite end of a circle, if circles have any ends, but I hope you know what I mean. Now, the second step and the first actual step after the initialization is to apply a random distortion. We will apply it by creating a vector of a constant magnitude or length, but at a random direction. So the target simply moves to a random direction, like this. And now we are ready to the third step of the algorithm. Pull it back to the perimeter of the wander circle. As you remember, the agreement was the target will always be at somewhere on the perimeter of the wander circle. So here it is. And it's a nearly complete first cycle of the algorithm. The step number 4 now is to apply the seek behavior pattern for the agent to direct to the target. So as you can see, our agent has just performed a random turn right. Now, the steps 2, 3, and 4 will be iterated, will be repeated many times. So now we go back to application of a random distortion somewhere. Please note that it can be in any direction. It can be also to the inside of the circle. Now the target is pulled out to the perimeter, but the main assumption that the target ends up at the perimeter is kept. Okay, and of course seek the target, and the third cycle will render the target move to the left or counterclockwise. Of course, it will be also pulled back to the perimeter. What is important in this algorithm is that left or right turn will be persistent. Once you start a turn right, it will take several cycles before changing this turn into a turn left. And this will create a more fluid, more realistic and more natural movement. Okay, so all this looks pretty much logical, but the big question is what kind of programming approach we should apply to get all this working in C++. So, the programming approach is based on two considerations. First of all, the Wander circle will be centered at the position 0, 0 of the coordinate system, and its radius will be equal to 1. This simplifies a lot. First of all, the initialization of the target position, which was here, becomes very simple because, as you can read from this diagram, the initial coordinates of the target are 0, 1. Now, application of a random distortion is just adding to the target a vector with two random coordinates. You can scale this vector differently if you wish, but this one should work. Please note that random here is a function returning a random number in range between 0 and 1. Okay, the next step, pulling it back to the perimeter of the Wander circle, is surprisingly simple because whatever are the coordinates of the target after application of the random distortion, if we normalize the coordinates of the target by the definition of normalization, normalized vector is a vector at the magnitude of 1. So if we are talking about coordinates, a vector with magnitude 1 will be somewhere on the perimeter of this circle. So a very elegant implementation. But of course, the main question is, all right, this Wander circle, it's very nice, but it should be at the Wander distance in front of a moving agent. It should have a Wander radius, all right? So what we need is to introduce additional step here. Reposition the Wander circle. And the code for this is here. So we will now, when we have this target position calculated in the small circle in the center of the coordinate system, now we can do the following thing. We can find the real target in front of the guy, in front of the agent, by adding together the position of the agent, the Wander distance multiplied by normalized velocity vector, and okay, don't worry, I will show this on the graphical diagram. So first of all, we have our agent somewhere here. Now we know its position, we know also the direction in which it is heading, and this direction is the velocity vector normalized. Okay, normalized velocity vector will show the direction in which the agent is moving, but it will not provide additional value for the speed. So the normalized velocity vector can be multiplied by what we call the Wander distance, and in this way we can get the first vector, the Wander distance, position of the agent, plus normalized velocity, so direction of the movement, multiplied by the value of Wander distance, gives us the position of the center of the circle. Now, to get the right circle radius, we just need to scale or multiply the current coordinates of the target by our desired wander circle radius. Here it is, and we will also move this circle here. Done. This is the real position of the target, and here is the corresponding C++ code, maybe pseudocode. As I mentioned before, this code will not be one-to-one applicable for your GFC projects, but it will be very, very, very close to it. Okay, so position plus normalized velocity multiplied by wander distance plus target. Please note that the target is the coordinates, pair of coordinates of the target point multiplied by wander radius to scale to grow this wander circle to its desired size. And now we are just one step from the end of this algorithm. We need to call one of the previously described behaviors, seek, providing the real target as the target for the agent to seek, and perhaps providing a special speed. In most cases, wander speed should be a little bit lower than regular seek or flee speed. As you think about it, if I am a rabbit just nibbling some grass and wandering around, I won't be particularly speedy. But when I spot the fox, I will run really, really quick. So the speed should be different from seek/flee speed, different and lower. Please note it's quite important that steps from 2 to 5 should be executed each frame on a frame-by-frame basis, and step number 1 is just the initialization. It's a one-off initialization. The last of the behavior patterns presented today is called obstacle avoidance. It's about an autonomous agent negotiating its way across a complicated environment in which we have various obstacles. And as the name suggests, the goal is to avoid these obstacles. So the first step is to create a rectangular stripe in front of the agent along its motion axis and at the width are identical to the width of the agent. Now, for each obstacle, we will find its distance from the motion axis, shown red, and the position along the motion axis, shown blue. Now, we will discard every obstacle which, first of all, is behind the agent. So, for example, this one. It will have a negative position along the motion axis. We will also discard every obstacle that is beyond agent's field of sight, so too high on the positive side of the motion axis, so this one. Then we will discard every obstacle that is further from the motion axis than half of the width of the agent plus the radius, so it's outside or sideways from the strip, so it's this one. From the remaining obstacles, if there are any, only the closest to the agent is taken, so this one. And now, when we are guaranteed to be left with at most one obstacle, a small sideways steering force is generated. Thank you for watching, and don't forget to watch the final installment of our Autonomous Agent series, which will be about swarm intelligence. Thank you.